Well, a warm welcome, everybody. Thank you for joining. As usual, get yourself ready with a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, we're going to start a small summer series of calculus problems. Basically, the idea is I had a student. I won't name them, but I wrote some problems for them. They were an AP Calculus BC student, having skipped AP Calculus AB. So that was a bit of a fast-paced tutor-client relationship. But nonetheless, I wrote plenty of practice tests and questions for the student. So you're going to be learning with examples that they themselves used. I would like to mention they got into the college that they were hoping to get into, which is always an awesome thing to see when you've worked with somebody and they're so hardworking in so many other areas, and it pays off, man. So enough reflection. Let's take a look at the problem for the day. We have a problem from the topic of implicit differentiation. You can go ahead and pause the video if you'd like to give yourself a chance to work on this, which I encourage you to do that first. Those are the questions we want to consider this curve, and I have questions A, B, and C for you. Like I said, feel free to pause the video, give yourself some time to work this out on your own. So when you're ready, come on back, see how we do it here. Without further ado, let's get started. So this is an implicit differentiation problem because we have an equation and a curve, not a function, but a curve that is defined with lots of y terms and x terms all over the place. So not a one-to-one function. And first step is to take a derivative. So whenever we're working with these equations, we just take a derivative of both sides, right? So we're going to end up with 6y squared. Let's do a little d dx, put some brackets there. And then we're going to do a d dx of 1, which should not surprise you what that does be. So when we do a derivative with respect to x, we have to use the chain rule on any of these y terms. So we have dy dx being multiplied. Everything else we treat it kind of the same as we would with an x. The power rule applies, 6y squared. And let's move on because next we have a product. So we're going to have to use the product rule. It's going to be plus, and let's put a parentheses just so that we can have our product rule stuff going on. How do we do the product rule? Well, we take a derivative of the first thing, multiply it by the second thing, and then we just switch. We add the product of the first thing, just leave it alone, and the derivative of the second thing. So the first thing here is my 6x squared. I'm going to call this 12x, that's the derivative, and we leave the y alone. You don't have to do anything to it, you just have to place it. It's so easy. A lot of this mathematics is just placing things, especially in calculus. You're really just placing things appropriately. Other than that, what am I doing? Multiplying by 2, and then we just add 6x squared. You can leave it alone, you don't have to do anything to it, and multiply by dy dx. Okay, that's that little product rule. Let's continue. We have some power rule. Derivative of 12x squared is 24x. That's pretty straightforward. And then the final term on the left side is 6y, so we'll have 6, and of course we multiply that by dy dx. Now on the right side, derivative of 1, no surprise, it's just 0. Okay, so how do we solve for dy dx here? We find dy dx by getting it alone. And since there's no tricky negative stuff going on with these parentheses here, I'm just going to dissolve the parentheses. It's like a layer of protection just in case there's any extra things you have to do, but we didn't have that situation here. It was just plus and plus. Let's move everything that does not have dy dx over. So I'm looking at this term here, and I'm also looking at this term here. Basically, anything that didn't have y is not going to have dy dx. So we're going to move that over. Let's do it carefully. Subtract 12xy and add 24x to both sides. And that gets rid of any terms that do not contain dy dx here. So what we can do is we can factor dy dx, and on the left side, we'll be left with 6y squared plus 6x squared plus 6. Notice that all of the terms which had dy dx in it I'm basically putting together. And the sign is important, plus 6x squared and the plus 6. If there were minus, then we would need to have the minus in the parentheses. Okay, and on the other side, we have this negative 12xy plus 24x. If you're noticing that things are divisible by 6, you're absolutely correct. So we'll reduce that in a moment. What do we do to finish this off? We have to divide both sides, and that gets the dy dx by itself, right? Anything divided by itself, other than 0, of course, is 1. And now it's time to simplify that a little bit. We can divide everything by, 6 is the largest number that we can divide everything by. So negative 2xy plus 4x. Or if you put 4x minus 2, same thing. Over just y squared plus x squared plus 1, I guess. Yeah. So at any given moment, if we have a point on the curve with an x and a y coordinate, it has to be on the curve. This equation will tell us what the slope of the curve is at that point. Okay, let's move on to part B. It says write an equation of tangent line. Now, if you've seen any of my calc videos and you've ever come across this phrase, which does happen quite often, you know exactly what I'm going to say. As soon as I read equation of tangent line, immediately on a free response problem for AP Calculus, you should write out y minus y value equals m times x minus x value. This is the point slope equation. It's nothing fancy. It's just the point slope equation of a line. But it's useful here because it's going to tell us a description of the curve at some point. And what point did they specify? All points where the curve is horizontal, which tells us something very important. Horizontal means what? It means like flat, right? Which means the slope equals 0. So, by the way, that's our m, in case you were curious. So we're going to have y minus y value. That's why it's useful to write this out. And then whenever you get values, you can plug them in. 0 times x minus x value. So really, we're just going to get a flat y value. We're just going to get that y equals the y value. That's our equation. So if we can find the y value where it's horizontal, right? Where it's horizontal. If we can find that y value on the curve, then we're good to go. So how do we describe the slope being equal to 0? Well, we just did something in part A that has us result in an equation, like I said, a little formula for the value of the slope at the curve. So that means we want dy dx to be set equal to 0. And whenever a fraction is 0, right, this is a fraction here. Whenever a fraction is equal to 0, if you need a reference on fractions, again, I have a great video that I just made recently about fractions using cookies. So it should be very insightful, I'm sure. Anyways, you'll know that the top of a fraction has to be 0 in order for that to be the case. Now, of course, we can't have the bottom be 0, but that's not a concern here because the denominator of this fraction is always going to be greater than 0. That's because y squared cannot be negative, x squared cannot be negative, they're 0 or greater. And then if we add 1, this is definitely greater than 0. So we have no concern for the denominator being 0. That would pose a problem, but it's not going to be a problem here. So we just consider when the top of a fraction is equal to 0. Which means we consider when negative 2x plus 4x is equal to 0. Now, this seems to have lots of solutions here, so let's factor this a little bit. We see the common x term. I'm going to take out the negative 2x. That's going to leave us with y minus 2 equals 0. So either x equals 0, or perhaps y equals, I should say y minus 2 equals 0, which of course implies that y equals 2. And here I should say that negative 2x equals 0, which implies that x equals 0. But I think you guys are clear with that. So what do we have to do here? We have to check to make sure that this actually occurs on the graph. The derivative equation dy dx, it does not really have the information about the curve itself and what values the curve is at. It just tells us the slopes. So we still have to check to make sure that these theoretical solutions for when the curve is flat actually occur on the curve. Makes sense, right? So if y equals 2, we'll try this one first. Let's plug in y equals 2. Well, then we're going to get 2 times 2 cubed plus 6x squared times 2 minus 12x squared plus 6 times 2 equals to 1. I'm just plugging the y value of 2 into the original equation, and yes, we're going to get an issue here because we have plus 12x squared minus 12x squared and plus 12. Definitely these things do not equal 1. So 28 does not equal 1, of course. Therefore, y does not equal 2. 0. Well, we also have to check that and plug this in. If x equals 0, this means that 2y cubed, some of the 0 terms just get eliminated. The second and third term get eliminated. Plus 6y equals 1. Now, this does not have an obvious solution. This is a cubic equation. Even if you were to use like the rational root theorem and try to factor it down or try to break it down, unfortunately, the root here does not seem to be rational. There is a pretty tricky cubic equation, much like the quadratic equation, but that's not taught typically at a calculus level. It's from the Cardano formulas. So what we would have to do here, our best bet, if we were not allowed a calculator on this question, I don't remember if I allowed my student a calculator or not. So go ahead and use a calculator. You should get a value. But if we're not allowed to use a calculator, what would I do personally? I would sort of use the intermediate value theorem. I would move everything over. And you could also use Newton's method, for approximating zeros. And yeah, from here, I would basically just plug in maybe like 0, right? If this is our function, say f of y, or rather f of 0, equals negative 1, and f of positive 1 equals 2 plus 6 minus 1, which is 5. So clearly there's a 0 somewhere between 0 and 1. If I wanted to get more specific, I guess I could plug in 0.5, 1/2. That would be a little bit tricky. If you're not that great with multiplication, you have to be very careful. You don't have to be as quick as I am, but you just have to be very careful and you will get the correct answer. So 0.5 cubed times 2, that's going to be 1/4. And this is going to be 3 minus 1. So we have 2 and 1/4, or I guess we can say 9/4. Okay, so we know it's somewhere between 0 and 0.5. Do you understand what I'm doing? I'm basically narrowing my window down to find out where it would be at. And let's see, I might as well, in the interest of time, I wanted to try 1/4, but I have a feeling that's not going to do it either. Let's use a quick little calculation. I guess I wouldn't want to round it to 0.2. 0.165, I think is a good approximation. Y equals 0.165, approximately. That's our approximate equation of tangent line. It's a flat line, no surprise. Slope is 0 because it's horizontal. Okay, let's move it along. Part C. The line through the origin with slope -1 passes through the curve at some point P. Find the x and y coordinates of P. So the line through the origin, what is that? Y equals kx, or k is the slope, or you could just say y equals mx. Why am I making it more complicated? Y equals mx. But it has a slope of -1, so that's our m. Y equals -x. And we're going to use this into the curve because we want to see where it crosses, so we want to see where this is present on the equation for the curve. So you can do this by plugging in negative x for your y, 6x squared times negative x, plus 12x, oh wait, minus 12x squared, oopsie, minus 12x squared, plus 6 times negative x equals 1. Okay, so it's going to give us another cubic here. Minus 6x cubed and minus 12. Lots of minuses here. Minus 6x equals to 1. I guess we can move everything over to the other side and have positives. Oh, we can also combine like terms here. We have 8x cubed plus 12x squared plus 6x and plus 1. There you go. Turn your negatives into a positive, yeah? And then, since this is a cubic, again, I don't think the rational root theorem is the best way to go here. I'm getting more and more convinced that this was a calculator problem when I wrote it. So go ahead and feel free to use a calculator, because again, solving a cubic equation is not necessarily that easy. If you want to try to use the rational root theorem, be my guest. Okay, yeah, it turns out to be negative 1/2 is the solution. Now, keeping that in mind, there are some other solutions to this, but we're going to have to go back and confirm that they are not solutions to the original curve. So let's go ahead and use synthetic division, whatever method you really want to divide this. We have a negative 1/2 in the box. You guys know the synthetic division process, right? It's going to negative 4, 8, negative 4, 2, negative 1, 0. And so we're left with a quadratic that can be solved, and we will get 2 other x values as roots. In fact, let's do that. And you might recognize this, hopefully you recognize this. This is a perfect square trinomial. So it turns out x equals negative 1/2 is the solution to those as well. So negative 1/2 is a repeated root. It is the solution, not just a solution. It is the solution. And therefore, we have a y value, which is equal to negative 1/2. Because y equals negative x is the value, or the equation of the line that intersects with the curve. And so the point P is negative 1/2, 1/2. Okay, not too bad. Good clean family fun there. Now, I recognize that this did take a little longer than I originally predicted. I guess we should maybe expect that from the other questions in this summer series of keeping you fresh with calculus. I'll see you guys next time.